with Elad, who will tell us about open Gromov-Witten invariants for even-dimensional Lagrangians.
Okay. Thank you for having me. So I'll talk about, as Pazit said, open Gromov-Witten invariants for even-dimensional Lagrangians. This is mostly joint work with Jake Solomon. I have a problem with the slides. Okay, sorry. So the setup is a symplectic manifold and a Lagrangian submanifold, and we need an omega-tamed almost complex structures. And the objects that we are trying to that are in play are holomorphic disks with Lagrangian boundary conditions. And to define the invariants, we need additional data. So we need boundary marked points on our Lagrangian. These are the points our disk will be constrained to pass through. Constrain cycles away from our Lagrangian. Those are the constraints that the interior of the disk should pass through. And a relative homology class beta representing the degree of the disk. So you can see in the picture that our goal is to count geomorphic disks of degree beta passing through K general points on L and intersecting the interior constraints. Now, there is an issue with defining counting invariants of geomorphic disks, and is that as we vary the geometric constraints that the disk have to pass through, what can happen is that the disk can bubble, and this is not stable. So if they bubble and you change it a bit more, they vanish. And so, for example, if you change the marked point, the count can change. And this is different from closed Gromov-Witten theory. In the closed case, the boundary strata is of codimension 2, so you can generically avoid it. But the boundaries of the moduli space of geomorphic disk has a codimension 1 strata, so you cannot avoid it. And bubbling will occur as you vary the parameters defining the equations. So sometimes you can handle these problems if you have symmetries of the pair of the Lagrangian and the symplectic manifold. For example, if the Lagrangian is a fixed point of the anti-symplectic involution, then in low dimension disk that bubble comes in pairs with opposite signs, with opposite orientation in the moduli space. And then this counting of bubbling cancels, and you can define open Gromov-Witten invariants. And this have been done in dimension 2 and 3 by Liu, Shu, Solomon, and Georgieva, for example. But if you require more boundary constraints in dimension greater than 3, then this cancellation fails. So the main result that I want to present is that in higher dimensions and with multiple marked point, one can define open Gromov-Witten invariants. And under either of the following assumption. So when L has a rational homology of a sphere, then one can define open Gromov-Witten invariants, and the interior insertion is a relative homology of the Lagrangian. If you have a symmetry, when the Lagrangian is a fixed point of the anti-symplectic involution, then one could say reduce a bit the topological assumption on L. So in low dimension, for example, this allows you to define invariant for in dimension 2 for a Lagrangian torus if it's a fixed point of an anti-symplectic involution. So, and this is joint work with my advisor, Jake Solomon. And in in dimension 2, those invariants that we define, they recover previous classical real enumerative geometry invariant, Welschinger invariants. So if A is a class dual to a point, then summing over invariants of all degrees that double to degree D rational curves recovers a Welschinger invariant. So in the case where the Welschinger invariant is defined, then we recover it. And this is immediately shows that we can give example where this open Gromov-Witten invariant with multiple boundary constraint is actually non-trivial. And in an upcoming work, I also show that one can define non-vanishing invariant with multiple constraints, point constraints on the Lagrangian in higher dimension. For example, in the quadric hypersurface, you take the Lagrangian to be the fixed point of the conjugation. It's a sphere, and you can define counting invariants with Lagrangian and with point constrained on the Lagrangian. So this is an example of the invariance with 3 point constraints in the Lagrangian and point constraints away from our Lagrangian, which the number is for the is to get the right degree, the right dimension of the moduli space to get a finite count. So for degree beta equals 1, the invariant is -2. And this computation was implicitly already done by Huttenberg and Tukachinsky, which also computed Gromov-Witten invariant of quadrics. For the degree beta equals 4, the invariant vanishes, and you can actually prove it geometrically, why it has to vanish in this particular degree. But as you can see, as the degree goes up, the number grows very rapidly. So now let's try to talk about how one would get those invariants and how so this is basically following ideas of Fukaya or Otto Ono. Solomon and Tukachinsky, they put forth a strategy to define open Gromov-Witten invariant using cyclic unitary infinity algebras. So the Lagrangian submanifold gives you an A infinity algebra, which are operations on the defined using counts of geomorphic curves. And you also need a pairing, which plays nice with your operation in a cyclic way. And the infinity algebra needs to be unital in order to define those define open Gromov-Witten invariants using the infinity algebra. And what you want to use to basically to get an invariant count is for your point constraint to be a bounding cochain. So given an infinity algebra, you can deform your infinity operation by inserting degree 1 element of the algebra. And the Morel-Croton equation asks that the zeroth deformed operator will be some multiple of a unit. And if you manage to find this B of degree 1 that solves this equation, then it's really important also in floor theory, you can define a chain complex using the deformed operator and giving you a chain complex. So what you can do with a cyclic unital infinity algebra, and what has already been done is if you can just extend the coefficient ring of your infinity algebra by tensoring it with graded commutative algebra and extending everything multilinearly to all the operators. And then you use the formal parameters that you introduced, you assign to it a degree 1 minus n. And this basically says that if you multiply it by a point class of degree n, you get a degree 1 element in your infinity algebra. So a point constraint multiple of the formal parameter is a candidate for a bounding cochain in your new infinity algebra. And what Solomon-Tukachinsky showed that you can use a normalized bounding cochain to define a generating function, the superpotential of those open Gromov-Witten invariants. And then you can use this generating function to read off. You read off the coefficient of this generating function, and this will be a well-defined open Gromov-Witten invariant that no matter what was your original point constraint you chose to get the same count. And they define count with basically the same topological assumption on the Lagrangian as the work I presented, also with jigsaw. So the problem in even dimension is if you're working with a graded commutative ring, the coefficient will just vanish. And then you can't use and then you won't get multi-point invariants. So you have to drop the graded commutative Witten to work. But you can still work over non-commutative rings. So you have to think a little bit how to extend the definition to in the non-commutative section, but still get cyclic unital infinity algebra. And after you do it, you still have to obtain bounding cochains for the new A infinity algebra in order to get invariants, to define those invariants. So the way to do it is following Fukaya Ono is to solve the Morel-Cartan equation inductively on a discrete filtration. So so the inductive step is given bounding cochain that's up to the truncated by the energy infinity algebra. One would get an obstruction class. And then if you show that if you in the relevant obstruction theory, and then if you show that it vanishes, and you can define for all energy, then you can define the then you can find a bounding cochain. But there's the obstruction theory is just harder in the non-commutative setting, because you get an additional element that's of the bounding chain squared with itself, or morally it is, that gets in the way with showing that the obstruction vanishes. And this element, we have shown that it lives in a certain page of a spectral sequence converging to our obstruction cohomology. And the E1 page of this obstruction is in the top cohomology of the Lagrangian. So, and what we shown that if you put a non-trivial filtration on your formal parameter S, then the spectral sequence degenerates at the relevant pages, and you get an obstruction to solving the Morel-Cartan equation. So, but if you give the formal parameter zero filtration, then the relevant page for this non-commutative obstruction will vanish. So you should try to use a filtration to give this variable a zero value, but then you get other problems, which is that the Morel-Cartan equation won't necessarily converge. You get an infinite many terms a priori at any energy level, and the Novikov completeness doesn't guarantee convergence. So you need to introduce the new notion of pseudo-completeness, which is that an A infinity algebra is pseudo-complete with respect to a second filtration if adding enough inputs. So this is measured by this new filtration, eventually pushes the output to arbitrary high energy. So you do get convergence, and we showed that our A infinity algebra that we use satisfy this pseudo-completeness property. So this allows you to show that to reduce the obstruction theory to a question about the topology of the Lagrangian, and then if it's a rational homology sphere, then this obstructions solving the Moeller-Cartan equation vanishes. So in the remaining time, I will talk about an upcoming work of mine, which shows that you can really compute those invariant because they satisfy recursive relations similarly to the closed Gromov-Witten invariant and to the commutative open Gromov-Witten invariants previously defined. And this is that the generating function for those invariants satisfy the open WDVV equation. And this means that you can compute the invariant recursively using a small number of base cases because those generating functions are so over the WDVV equation makes this such an overdetermined system, then you basically, if you know some of the coefficient of the generating function, you basically know them all. And similarly to what Solomon and Tukachinsky showed for the commutative open Gromov-Witten invariant, they also satisfy a certain axiom, similarly to the closed Gromov-Witten invariants, that allows you also to use them for recursive computations. And this allowed me to revisit a work by Huttenberg and Tukachinsky, where they computed the open Gromov-Witten invariants of smooth quadric hypersurface. And so in even dimensions, they all the invariants with multiple point constraints vanish in their case, but this is no longer the case in the open Gromov-Witten theory. And there's something interesting is that if you take the commutative setting, then for even dimensional, for Lagrangians, oriented even dimensional Lagrangians, you basically have a result that the quantum cohomology is injective in the closed quantum cohomology. So in the when the coefficients are commutative, then the closed Gromov-Witten invariants basically determine all the open Gromov-Witten invariants. But working with non-commutative coefficients, you basically get invariants that are not determined by they are determined using the open WDVV, but not entirely by the closed Gromov-Witten invariants. So thank you for listening, and I'll be happy to answer any more questions.
So thank you, Elad. Are there any questions? So why these examples of again Can you do other examples other than n equals 6 and these betas?
Yes, I can do other examples. Well, one reason is kind of lame is that Rutenberg and Tukachinsky did a really good work. So it was easy to do it because like the strategy to compute this is you need some geometric input of for example computing one, in this case you need to compute one open Gromov-Witten invariant, and then they are all recursively computed from them. So they already did work for the, like most of the work for the computation, so it was easy. So like I have another work that I'm doing is to try to compute invariants in low dimension and dimension 2 that can't be computed, that couldn't be computed before because you needed this empty symplectic involution. Computing invariants of spheres in low dimensions that are not fixed point of the anti-symplectic involution, for example. So, but the real reason that I chose, like I did this, is just because it was like a low-hanging fruit, not. But it's like it's already kind of cool. Is that with those invariants that like you sometimes see like weird phenomena like the vanishing of the degree 4 invariant here, and then you can try to think why it happens, and like in this example it happens because if you have a holomorphic disk in the quadric, you can double it to get a holomorphic curves in the quadric. And this is a holomorphic curves in CP5. And so this means that because of the degree, it has to be contained in CP4, in some CP4 and CP5. And but then CP4 and CP5 is already determined by 5 points. So it's like obvious that this invariant will vanish. And this also tells you why, like this, after that it won't happen because there won't be any like weird geometric constraints. So like playing with like computing interesting invariants sometimes give you like cool geometric problem, even though you don't need to you don't need them to define those invariant. You only need like one, but you can see other stuff appearing from the invariants themselves.
Okay, great, thanks.
So is there time for another question?
Yeah, we have
Yeah.
only 2 topics.
Yeah, so I have a bit of a technical question, Elad. So how I understand you use filter the infinity Fukaya type categories. Yes. So how do you ensure the filtration that they are filtered? So what's the actual? So you use perturbations of some type or Hamiltonian perturbation? How maybe I just don't know.
So like the well, I kind of hid it a bit, but the modelized spaces themselves, like the work doesn't really touch on it. So I kind of use model like in the quadric example, or you have it's like a really kind of you have a homogeneous action that means that holomorphic curves that the modelized space is really nice, and it's a smooth submersion, and so you have but like the algebraic theory is basically most of the work won't is not going to be harder if you I don't know, introduced Carnot structure or any other thing to handle the regularity of the modelized spaces. I'm not sure if I answered your question.
Yeah, almost. So my point is that there are some specific difficulties to do filter the infinity algebras, and there are maybe a few techniques to do this, but I was just curious which one appears in your thing. Maybe, if I understand correctly, you're using something that Fukaya and his collaborators are
So
doing. Um,
Yeah, but yeah, if you wanted to work in full generalities, then yes, uh, but uh, uh, but like in this example, you can
Yeah,
kind
I
of
understand. Okay. Yeah, so I agree. In examples, it's quite different because there
yeah.
are some. But okay, thank you very much. Yeah, it's pretty clear.
Yeah.